Welcome back, everyone. Oh, yeah, question.
Is the square still there in
Huh?
the last line? Is the square still there in the last line, or does it work?
That's a typo. That's a typo. Thank you. As Piotr said, if you guys get 90% of the proof, that's about the best they can be asked for because it's only 90% correct. Okay, let's get started again. Thanks everyone for your attention. So we're using the iPad so that we can make sure we broadcast on Zoom, and I apologize to the Zoom audience a little bit, but I wanted to put a little bit of history and some basic stuff up on the boards so we can keep track of it. I recognize that we have a lot of different backgrounds here, and I'm using some sort of probability notation and facts a little bit freely, and I know that that's probably not so familiar to some of you. So if I use notation you don't know, even if it seems like a stupid question, please ask. I don't mind defining notation. We don't have to get through everything that I wrote in this notebook. So I just want to do a really brief clarification of a couple pieces of notation. So sorry, Zoom guys, I'll be back in just a second. As I said, if I take the expectation over a discrete set of points or vectors, I'll usually write expectation sub I, xi, where the x's are the guys in that set of points or vectors. And that just means the average, it's a discrete average. Second, I use this notation for two vectors in D dimensions. I use this notation like UV transpose. I was often writing x minus expectation x times x minus expectation x transpose. And that's the outer product. So it denotes the dimension by dimension matrix, D by D matrix, where the ijth entry is the ith entry of U times the jth entry of V. Okay? A basic fact that I'm using over and over again about total variation distance is that if I have two discrete sets of points, let's say x1 through xn and y1 through yn, and usually I will just confuse x1 through xn, the discrete set of points, with the uniform distribution over that set of points. Those two things are the same in my mind. The total variation distance between the uniform distributions is less than epsilon if and only if I can pair up the points so that xi equals yi, maybe after reshuffling indices, for all but an epsilon fraction of those points. And that in turn is the same as saying that there's a coupling between the two uniform distributions so that when I sample them jointly, according to that pairing, they're equal with probability at least 1 minus epsilon, or not equal with probability at most epsilon. So I'm just interchanging freely between all those consequences of total variation distance. The definition of a covariance matrix, so this is if I have a high dimensional random vector, let's call it x, then the average of the outer product of x minus expectation x and x minus expectation x is the covariance matrix. And just to interpret a covariance matrix, what does it mean? If you have a random vector x, then the covariance matrix captures all of the information you need to know to understand the variance of that random vector x projected in any one-dimensional direction. So if I take any unit vector v, I project my random vector after centering in the direction v, and I look at the expected square, that's equal to the variance of this real valued variable, which is x projected in a direction. That variance is at most 1 for all vectors if and only if, by definition, the covariance matrix has all eigenvalues at most 1, is upper bounded by identity. These are just all equivalent statements about variance of random vectors in high dimensions. Okay. Lastly, where we were last time, we labored a great deal to prove this identifiability lemma, and then the identifiability for robust mean estimation followed pretty quickly as a consequence of this lemma. The lemma was that if you have two random vectors in D dimensions and their covariances are at most order identity, and their total variation distance is at most epsilon, then their means are at distance at most O of root epsilon. Okay, that's where we were. Questions? All right, I promised that this talk was actually about algorithms, so we've got to talk about algorithms. And it was actually about the sum of squares method. And we said that a key feature of the sum of squares method, one point of view you can take on it, is as a proof system. So let me switch gears and talk about SOS proofs. So you're probably familiar with formal proof systems from maybe high school geometry. in high school geometry, you prove these formal statements about, how if an angle has some properties or a triangle has some properties, and you derive those statements by applying a small set of rules to derive new statements from previously proven statements. And the sum of squares proof system is sort of the same way. You can view it as applying a series of rules. I'm going to take a more one-shot point of view at it, but in the sense that every proof will have sort of one step. But it's still the same spirit that there's sort of a formal rule that allows you to derive inequalities, and anything that you can prove using that rule counts as a sum of squares proof. So it's a system, a proof system for proving mathematical statements of the following form. If you have some polynomials, P1 through Pm. Now let's say that these guys are multivariate polynomials with real coefficients. So these guys, so x is really x1 through xn, and the p's are n variable polynomials. The system for proving statements like this: when all these polynomials are non-negative at a point x, then some other polynomial p is also non-negative at x. Now, why do you want to prove statements like this? Well, polynomials are interesting in their own right, but polynomials are sort of a universal mathematical language. Many of you have probably encountered polynomials, one variable or many variables, in the course of doing other computational, mathematical, statistical work. And the point here for our purposes is that lots of interesting mathematical statements can be expressed in that form. So we like statements about polynomials in their own right, but also because we're going to express other statements in this language. And then we're going to leverage the power of the sum of squares method to make use of these formal statements. So you'll see what I mean in the next 20 minutes. Okay, so what is a sum of squares proof of a statement like this? Well, what should a proof do? A proof should convince me of the truth of a statement. Here's one way I could be convinced. Suppose that I can write this polynomial p that I want to conclude something about. Suppose I can just syntactically rewrite it in the following way. The summation over all possible subsets of these guys, which I'm going to start calling axioms. For each subset, the product of the axioms in the subset and then times some special polynomial associated to the subset with the constraint that this guy is a sum of squares of other polynomials. Let's say S, I don't know, indexed by j's, just some other polynomials, the sum of the squares of them. Now you see where the name comes from. So suppose that I presented you with the polynomials QS. I told you those polynomials. Those constitute, I claim, a proof of this statement above. Why is that? Well, let's remember that squares of real numbers are non-negative. If you evaluate a polynomial with real coefficients at a point in Rn, you'll get a real number. So for every x such that these guys are all non-negative, let's look at this thing term by term. Well, since these guys are non-negative, this product is non-negative. And for any x, no matter what happens with the p's, QS is non-negative. It's non-negative everywhere. And therefore, if I can write P in this form, it's a certificate that P is non-negative whenever P1 through Pm are non-negative. That's a sum of squares proof. Sum of squares proofs come with a complexity measure. We're computer scientists, so we like to measure the complexity of things. If all the terms, and by a term I mean this expression, have degree, at most some integer d, we call it a degree d proof. Now, we're going to be interested in degrees that are relatively small. We're going to be interested in settings where the collection of polynomials is relatively large. And therefore, even though I've written here that you're allowed to sum over all subsets, typically we're going to be interested in the case that you're summing only over small subsets. So that you're taking a product of a small number of axioms at a time. And then you're multiplying those products by polynomials that are the SOS polynomials. Sum of squares we abbreviate to SOS. So SOS polynomials that are themselves relatively low degree. You'll see why quantitatively we do that in a moment, but it's because as the degree increases, the running time of algorithms associated to these proof systems also increases. So we're interested in polynomial time algorithms, and that typically means we're interested in small degrees D. Now, I can't introduce SOS without telling you at least sort of waving at the existence of a very mathematically rich history associated to this type of certificate of non-negativity of a polynomial. So way before Turing, like way back to Hilbert, late 1800s, there were questions about, say, can you write every non-negative polynomial in this form? It turns out the answer is no. It turns out you can write every non-negative polynomial in this form if you allow rational sums of squares, and that you can derive from that an analogous proof system. So this is all related to one of Hilbert's problems, Hilbert's 17th problem. Fields metals were associated with all of this. So this is out of scope to go into too much detail about the very rich history here, but there's a beautiful mathematical history associated with questions about sum of squares proofs. What's new in the last 20 years, maybe, is focusing very quantitatively on proofs of small degree, because as we will see, those correspond to polynomial time algorithms. Yeah. It had precursors up to 30 years ago, but I think this perspective, so my colleague here, Pablo Perillo, was one of the originators of this. He did it in the context of control theory, but he originated a lot of the algorithms associated to these things. And Lasserre is the other name associated with these. And so Lasserre and Perillo both came out with sort of this algorithmic point of view on sum of squares proofs in around 2000. Okay, so now let me tell you the main theorem that we're not going to prove today, but if you are at MIT and you want to take my course this fall, we'll prove it in lecture 2 of my course. The main theorem we're going to rely on to design algorithms. And I'm going to call it a theorem in quotes because I am going to leave out a few annoying technicalities. And if you want the real theorem, come to my class. So here's the theorem that relates sum of squares proofs to algorithms. Actually, this is a special case of an even more general result, but it's going to be good enough for our purposes for robust mean estimation today. And it's actually good enough for a lot more than just robust mean estimation. Well, let me do one thing, which is change this little n to a big N because I don't want to confuse this with the number of samples. This is the number of variables in the polynomial, and that will not necessarily be the same as the number of samples in some statistics problem. So I'm going to change that to a big N. Okay, theorem. There exists an algorithm with running time n times m to the O of d, such that given P1, I'm gonna call these guys, I'm going to introduce some more variables for my polynomials for reasons that'll be clear in just a second. So these are the same as before. They're just in 2 types of variables. They just have different names. So some polynomials, P1 through PM, and they have, let's say, bounded degree. So there are variables in x1 through xn1, z1 through zn2 of degree at most d. This notation just means the polynomials with real coefficients and those variables with degree at most d. Okay, here's the meat. If there exists a degree D SOS proof that P1, I'm going to start to drop the names of the variables here. P1 through PM non-negative. I'm going to write this notation implies, that means that there exists a sum of squares proof of this statement, implies that X is close to some vector V. Okay, so X is some list of variables, so you could think of it as living in R capital N, or capital N1 maybe. If these polynomials, if they're only simultaneously non-negative, if they carve out a region that's all close to some vector V, and I'll draw it in just a sec. Actually, let's just draw it now. So here's some vector V, and I'm imagining that I have a system of polynomials which are whose region of being all non-negative is all contained in a delta ball around V. It says distance. This distance is at most delta. Delta. Then the algorithm outputs y such that y minus v is less than delta. Okay, so let's interpret this. First of all, let's notice that the running time of the algorithm is exponential in capital D. So I would like to keep D a constant if the other things are growing. And in my contexts, the number of variables n and the number of polynomials m are going to grow with things like the number of samples or the ambient dimension. And therefore, I'm going to ask to keep this degree to be some constant in order to get polynomial time algorithms. Now, what's the idea here? The idea is that I wanted to find some vector v. You know, hint, hint, it's going to be like the mean that I wanted to estimate in robust mean estimation. I wanted to find some vector v, and I could characterize that vector by a system of polynomials in the sense that I knew how to write down a system of polynomials. Maybe the coefficients of those polynomials depend in some way on the samples that I got. I could characterize the vector that I wanted as the solution to this polynomial system, right, up to error delta. If I get anything that solves this system, then I've found V. Now, solving polynomial systems is NP hard, so that doesn't necessarily help me, right? If I just have a polynomial system that I need to solve to get the vector, well, what the heck am I going to do? The magic here is that if you can prove that your system characterizes the vector that you want within sum of squares, then the SOS algorithm will give you back some point that's close to V. It does not guarantee that it gives you a point that solves the system. But I don't care actually about solving the system at the end of the day. I care about things like robust mean estimation. Now, I'm not going to prove this theorem to you. It only takes one more hour, but we don't have it. It's an application of convex programming, in particular semi-definite programming, to prove this. So the algorithm under the hood will sort of write the polynomial system as a large semi-definite program. If you don't know what a semi-definite program is, it's like a linear program, but involving matrices. It'll write the system as a large semi-definite program. It'll throw that SDP into the ellipsoid algorithm and solve it. And the dimension of that SDP is depending exponentially on D. But that's all I'm going to say about how to prove this theorem. What I want to show in the next half hour is how to use this theorem to solve robust mean estimation in polynomial time. So our strategy to solve robust mean estimation. So remember that in robust mean estimation, I have two questions. Yes. Yes, good question. Yeah, so the SOS proof is the collection of Qs. And yeah, okay, and maybe another good question is, if I give you the Qs, how do I know that they're actually sums of squares? So I could give you the expression of the Qs as sums of squares, but it actually turns out that if I give you a polynomial, it's possible to check in polynomial time whether that thing is a sum of squares, can be expressed as a sum of squares. That task is also solvable by semi-definite programming. So exists a sum of squares proof means that, means that I can write, let's do it properly. It means that I can write delta minus x minus v squared. So this is the thing that would need to be non-negative for the inequality to hold. I can write this thing as this type of expression up here. So I can cook up Qs like this. Yes?
You have to be careful about the connectedness of the domain of where the polynomials are positive.
No, no. In fact, it's perfectly fine for that domain to be discrete. We're not going to talk about it. Actually, when we set it up, we'll have a discrete domain. A very common application of SOS is to combinatorial optimization, where the domain is definitely discrete. So that's not a problem. Of course, the convex relaxation you get is convex, so it's not going to have it's going to have a connected domain. Good question. Okay, the z variables are for some expressivity. So we'll see an example in a moment, but I'm going to, in order to use this tool to write down a polynomial system whose solutions are like the vectors that I want for robust mean estimation, I'm going to need some auxiliary variables in my system, right? I'm going to start using this like a programming language. So if I'm going to use it like a programming language, I want the ability to define more variables. It makes my life a lot easier. That's what I'm going to use the z's for. Yeah.
Is there any sense in which I should be thinking of that sum, sort of the composition of Px as a sum over sets as products of things in S as a Fourier decomposition or similarity theory instead?
That's a nice question. I think the sense in which it's quite different from a Fourier decomposition is that it's term-wise non-negative. So even though it's an expression in terms of low degree things, I don't, Fourier is about sort of decomposing something into orthogonal chunks. There's really no requirement that the terms in the sum be even close to orthogonal, and they certainly won't be in the SOS proofs we construct. I don't really have a definition of orthogonality to hand, but for any reasonable definition, they won't be. The importance here is the term-wise, the thing that's key is term-wise non-negativity. These are great questions. Keep them coming. The more questions you give me, the fewer inequalities you have to see. Okay. So here's what I think I'm going to do. I'm going to show you how to set up the polynomial system for robust mean estimation. And then I think instead of doing the whole SOS proof for robust mean estimation, which is going to be a bunch of polynomial manipulations that aren't that pleasant, even though they're mechanical, I think what I'm going to do is have us all remember that the only interesting steps in this lemma were Cauchy-Schwarz and a variance bound. And I'm going to show you simple ways to prove those facts using the sum of squares proof system. And then you're going to believe me or go read on your own terms that I can put those all together into a big SOS proof to prove the statement I need for robust mean estimation. So let's do the setup and just see how you can cast robust mean estimation in this polynomials language. So remember that I started life with this epsilon corrupted set of samples from some underlying distribution. So sadly, oh, you know what I'm going to try? I'm going to try, because it maybe is helpful to have the history a little bit available. Let's see if we can copy paste this. Is that too impossible? It's not so terrible. Thank you all for your patience as I learn to use this 10-year-old technology. Okay. So here's the plan. Remember that I have some x1. If I want to solve robust mean estimation, I have some x1 through xn. They're vectors in Rd. Okay, I'm going to start using, I don't know, k here because d now means degree. They're an epsilon corruption of some good samples, x1 prime through xn prime. And remember that x1 prime through xn prime had bounded covariance. And so my goal was to find some, let's say, some other collection of vectors so that the empirical distribution of my other collection of vectors had bounded covariance and it was total variation close to the x's. So here's what I need in order to use SOS to do this. Now, I'm not actually going to find those vectors. I'm going to find the final estimator, the final mean vector, but I'm going to conceptually use this idea of finding a collection of y's to build my polynomial system. That's what I need. A system of polynomials expressing, when I say expressing, I mean whose solutions are sets of vectors y1 through yn in Rk, such that the total variation distance from x1 to xn, y1 to yn is less than epsilon, and the empirical covariance of the y's yi minus expectation over I, yi is less than, I'm going to say, I won't explicitly write the constant. There's maybe a 2 or a 4 or something. So I want a system of polynomials that is solved by such a collection of vectors. And then if I could solve that system, which I'm not going to do, remember I'm going to use this SOS thing, but if I could solve that system, I'd be done. Right? That was what our identifiability proof said. Yes. Thank you. Yep, absolutely. Yes. Okay, here's how I'm going to do it. So this is basically like a programming class now. We're going to see how to program polynomial systems to be solved by a collection of vectors like this. So here are the variables in my polynomial system. Well, they're y1 through yn, and each of these guys, you know, they denote a vector in Rd. Or Rk, excuse me. So this is like yn1 up to yn k. So I really have n times k variables in here. Now I'm going to introduce some auxiliary variables that are going to be useful for my programming. First, I'm going to introduce some variables that allow me to express things like xi equals yi. Some 0, 1 type variables. And I'm going to have to do some programming to make them be 0, 1. But I'm going to have these variables that are going to be called w1 through wn. And we're going to think of them as 0, 1 variables. And then I'm going to need, and you'll see why in just a second. I need a variable to express the final the output that I want. So I'm going to call that, let's say, little x. And this is, again, x1 up to xk. So it's really k variables. And then I need I'm going to need just some more auxiliary variables. You'll see me use them in a second, just so that we get the types on the board. This is a big matrix of variables where I and j range over the ambient dimension k. You'll see why we need this in just a moment. Okay, so let me start programming. I want to express this idea that I want to express this thingy up here. So the first thing I want to do, so I'm going to start listing polynomials. The first thing I want to do is get the w's to act like indicators of something, 0, 1s. I can force the w's to be 0, 1s in any 0s or 1s in any solution to my system if I include in the system the constraint that wi squared equals wi. Of course, I talked about inequalities. This is an equality, but I can get this by adding 2 inequalities, wi squared at least wi, wi squared at most wi. Okay, so the only 2 real numbers that solve w squared equals w are 0 and 1. So anything that solves this will have the w's be 0, 1s. Okay, why did I want 0, 1s? Well, I wanted to be able to express the idea that the x's are equal to the y's most of the time. So I got to have some indicator to get my hands on for the x's being equal to the y's. And I'm going to do it like this. I'm going to include the constraint that wi xi, remember the x's are these corrupted samples, equals wi yi. So the y's are variables, the x's are numbers, they're samples, the w's are variables. If w is set to 1, it enforces that yi equals xi. If w is set to 0, it doesn't do anything to the y's. All right, so I'm building up Now I'm building up some meaning to these W variables. The W variables tell me something. I wanted this DTV, this TV distance thing, right? I wanted that the X's are equal to the Y's for most X's and Y's. Fine. Let me just ask most of the W's to be 1. Summation Wi equals 1 minus epsilon n. Okay, now I've asked that xi equals yi for 1 minus epsilon n of the y's. I don't know which ones, of course, but this tells me that the w's have to be turned on to 1 minus epsilon of the time. So this is starting to look good. So now I've got a system of polynomials which would be solved by a collection of vectors y1 through yn such that 1 minus epsilon fraction of those vectors are equal to the x's. I needed something else from my y's. I needed that they had bounded empirical covariance, right? The variance in every direction was at most 1. Now I need to express that. But are there questions about this so far? Okay, hopefully not. Oh, let me just, before I do the covariance thing, let me just express that the thing I want to output, this x, well, it's the average of the y's, right? That was the idea. The whole idea was I was going to output the empirical average of the y's once I found a good set of y's. But now I've got to do the tricky thing. I've got to program this bounded variance constraint. Now here's how I'm going to do it. I'm going to write the constraint and then we're going to interpret the constraint. So let me write it. You know what? I'm going, sorry. Instead of O of I here, I'm just going to make up a constant because it'll make our lives easier. I'm going to put, I don't know, 2 times I. Okay. So here's how I'm going to do this constraint. I'm going to say 2 times I minus, so now look, things changed a little bit here. I'm playing fast and loose between equalities between numbers, vectors, and matrices. Notice that these are numbers, or they're variables, but this is sort of a one-dimensional thing. This isn't a k-dimensional thing, so this is actually like k polynomial constraints. This is a one-dimensional thing. This is a k-dimensional thing. Now I'm going to do a k by k dimensional thing, so it's actually k-squared constraints here. K-squared axioms. So twice the identity matrix minus the expectation over I, yi minus little x, yi minus little x transpose equals bb transpose. Okay, what the heck is this? Remember that these b's were just a matrix of, they're really slack variables, if that's language that's familiar to you. This is a big matrix of polynomials in the y's and x's, but it expresses, if I plug in a solution, it expresses the empirical covariance of the y's. Okay? And now I've asked that as a matrix, if you take the empirical covariance of the y's and you subtract it from twice identity, that it can be expressed as the square of another matrix, BB transpose. Now it's a little linear algebra fact that I'm not going to prove to you, that if you take a matrix, M, if you can express it as 2 is an arbitrary constant here. Sorry, if you can write, let's say 2 identity minus M for a matrix M as the square of another matrix. Oh, that B is I was using for AA transpose. That's true if and only if M is upper bounded by twice identity, like all of its eigenvalues are at most 2. So that's a little linear algebra fact involving positive semi-definite matrices and Cholesky decompositions and stuff like that, which I don't really have time to prove to you, but you can look it up in a linear algebra textbook. And it means that this thing holds if and only if the covariance matrix of the y's is upper bounded. And in fact, in some sense, these b's are a certificate of that upper bound. So now we have a polynomial system. It is solved by a collection of vectors y1 through yn, indicators w1 through wn, another vector x, and a collection of slack variables b, only if those vectors y have the properties I want, and therefore the vector x is close to the true mean mu that of the underlying distribution that these corrupted samples came from. So if I could solve this system, I would be in good shape. Unfortunately, I don't know how to solve the system, and I have to use the sum of squares toolbox instead. So let me just capture what I just said as a claim. So okay, let's go ahead and denote this whole system as this whole thing. This is P1 through PM. Right, this is my polynomial system. And now I need, so here's my claim, that I just made. If y, w, x, and b solve P1 through PM, non-negative, then x minus, let's say, the average of the good samples is at most order root epsilon. So that comes by putting together the fact that we programmed into this polynomial system all the constraints on the y's that we wanted, together with our lemma from before, together with our proof of identifiability from before. Now, if I can get a sum of squares proof of this fact, right, now I'll be in really great shape. If I can get a sum of squares proof of this fact, then I can apply my SOS theorem up here to say that if there's, let's type check this. If there exists a degree D SOS proof that P1 through PM non-negative implies that X is close to some vector V, maybe I just need some squares here to make it really look the same. Then I can find a vector that's close to V. So I know it's true that if these guys make the p simultaneously non-negative, then X is close to some desirable vector for me. I just need a sum of squares proof of that fact. Yes. Good question. So each of these constraints is actually a lot of constraints, right? So here, implicitly, I mean 2n different constraints, 2 constraints for every index I. Let's actually write it out for these guys. So here I will have a polynomial that is wi squared minus wi. That needs to be non-negative. That corresponds to this. And I will also have a polynomial wi minus wi squared needs to be non-negative. That corresponds to this guy. So every time I have an inequality, I'm going to subtract one side from the other so that inequality is expressed as something greater than equal to 0. Then I throw that in as one of the p's. Every time I have an equality, I replace it by 2 inequalities. So I'm compiling the system of polynomial equalities and equations down into just a bunch of non-negativity constraints. But this is, this is the same kind of mechanical thing as taking like an LP and expressing it in standard form. There's nothing too exciting going on. But it's good to know how to do. And it's good, I should point out, again, that here it looks like 5 constraints, but each of these is a large family of polynomially many constraints, right? Polynomial in, say, the ambient dimension and the number of samples. Yes?
So for this theorem, you have to prove that the simplification using the rules of SOS.
Yeah.
Also prove that there exists a solution to the left-hand side in SOS. But we know from, just from the fact that the solutions came around from the sample, but you don't need to express that back in SOS.
No.
It's just a fixed x, such as P1 of x, P of x is non-negative.
I just told you. I mean, I told you because the good samples. Well, sorry, I did. That was a little rude. No, I don't. I just need that there exists such a solution. That's right. Yeah, I actually, that's a pretty good point. I left this out of the theorem statement, and I apologize because I did it I pulled it out of my head instead of checking in the book. Of course, you need that there exists a solution to the system. We can clarify exactly what that means later if you want. Okay. Right, so this polynomial system is solvable. It's solvable, in our case, it's solvable by the good samples, the y's that we said must exist. And I don't need to prove that in SOS. Nice question. Other stuff? No, it does not mean that there was. You can still run it and you might get something, but it does not tell you that there was a solution. Nice question. Okay, so the last thing that I want to do is I'm not going to do this whole SOS proof, but I'm going to show you a couple of the building blocks for it. All right, to convince you that the non-trivial inequalities that we used when we proved identifiability an hour ago are all captured by reasoning about squares of polynomials. Okay. So what non-trivial inequalities did we use? Well, I claim that we basically used the following. We used, remember when we had this setup where we had the variance of a random variable x minus y, and we needed to split it into x minus expectation x, y minus expectation y, and expectation y minus expectation x. So we did an inequality there. I'm starting with this one not because it's the most interesting, but because it's the simplest. And the inequality we used was something like this. A plus b plus c squared is less than some constant times a squared plus b squared plus c squared. We use this. Simple inequality. And in fact, by just iterating a proof of the following even simpler inequality, I would be able to prove this one. So I'm actually going to prove an even simpler one. A plus b squared is less than some constant times a squared plus b squared. Okay, really now the world's simplest inequality about real numbers. Can I prove this thing using sum of squares proofs? Well, here's what I'm going to do. I'm going to take the right-hand side minus the left-hand side and rewrite it over and over until I arrive at an expression that's a sum of squares. Now, that's what I'm doing, under the hood. In reality, I'm not going to do this left minus right thing because it's too painful, and I'm just going to start by like expanding things and rearranging. Okay, but really, this is not so complicated. So to prove this, we would take a plus b squared. We would express it as a squared plus b squared plus 2ab. And now we would use the fact that 2ab is, I claim that this is, here's some new notation for you, SOS less than a squared plus b squared, where SOS less than means the two sides differ by a sum of squares. Why is that? If I take a squared plus b squared minus 2ab, that's the difference between the two sides. It factors as a minus b squared, right? So that means that a squared plus b squared plus 2ab is SOS less than, I'll carry forward a squared plus b squared, And then I get another a squared plus b squared, which is just 2a squared plus b squared. Yes. By SOS less than, if P is SOS less than Q, I mean that Q minus P is a sum of squares polynomial. So P less than Q just means that Q minus P is a non-negative polynomial. But I'm talking about these special non-negative polynomials that are non-negative because they're sums of squares. Okay, so the meat here, why am I proving these like ridiculously trivial inequalities to you? It's because I'm showing you that they have special proofs of non-negativity. They're true because the left hand differs from the right by a sum of squares polynomial. And those kind of little building blocks, those are the key ingredients in these big SOS proofs that I would eventually construct for something like robust mean estimation. So it really behaves like programming. You start building up little building blocks like this, and then you can just use when you're designing sum of squares proofs, when you're using this in day-to-day research. Once you know that an inequality like this has a sum of squares proof, you forget the sum of squares proof, and you just use the inequality freely. And you know that you can eventually, if you have a proof in English that uses only inequalities like this that you know have sum of squares proofs, you'll eventually be able to compile it down to the set of polynomials that we talked about on a previous slide. Okay, so yeah. That's a great question. Yes, there have to be. There have to be because we know there are problems that don't, we're pretty sure there are problems that don't have polynomial time algorithms. So it's often the usual answer people give to this question is they say this weird statement that the turnoff bound doesn't have a sum of squares proof. That's a very loose way of speaking that I don't like so much, but maybe it's better to put it like this. There are statements that you can prove using the turnoff bound. So like one such statement is that if you take a, say a random 3-sat formula, that it has no fully satisfying assignments with high probability. That's a statement you can prove using the turnoff bound. And we believe very strongly that if I give you a random 3-sat formula, there will not be a sum of squares proof that there are no satisfying assignments to that formula. Because if there were such a sum of squares proof of low degree, then there would be a polynomial time algorithm to detect that random 3-sat's not satisfiable. So let me clarify what I said with one more thing. Actually, this rich history about polynomial proof systems that I talked about before, a conclusion of it is that for a slightly reformulated proof system, every true inequality has some sum of squares proof of some degree. Okay, so the proof system is, that's not a contradiction for what I said before, because for polynomial time algorithms, we're interested in low degree sum of squares proofs. So it's actually really beautiful. You get a knob that you can turn that's a trade-off between proving power and computing resources consumed, right? As I know for any inequality I want to prove, that I want to use, if I turn the knob high enough, if I turn the degree high enough, I can find a sum of squares proof. But that degree might be so high that the proof is no longer useful for polynomial time algorithm design. Now, this statement didn't really illustrate that because there's no asymptotics going on here. There's only 3 variables and the degree of the polynomials involved is 2. But now, for my last trick, I want to show you a sum of squares inequality where there are asymptotics going on. There's a large number of variables and the degree stays small. And that's going to be the most useful inequality in the world, which is the Cauchy-Schwarz inequality. Which you'll recall we used, I even wrote it in red, we used at some point in our proof of identifiability, so we better have a sum of squares proof of it. So what does Cauchy-Schwarz say? Cauchy-Schwarz says that if I have numbers, let's say A1 through B1 and, A1 through AN and B1 through BN, so I goes from 1 to n, that this sum is at most summation AI squared summation bi squared. And let me make it a statement about polynomials. So I'm going to square this side. Usually you would have square roots in Cauchy-Schwarz, but Cauchy-Schwarz square roots aren't allowed in my programming language. So I'm going to square everything so that I get rid of all the square roots. This is the Cauchy-Schwarz inequality. And I claim that it's SOS true in the sense that the reason this is true is because the right-hand side differs from the left by a sum of squared polynomials. And I don't know a better way to do this than just to write it out. So, and I actually have to look this up every time. Here's the expression. It turns out that summation ai squared times summation bi squared minus summation ai bi whole squared. My iPad does some automatic advancing thing, and it's a miracle that hasn't happened yet. Squared is equal to summation over I and j ai bj minus aj bi squared. Okay, I'm not going to do the algebra to check this. You can do that on your own time. Next time, you all eventually will teach a linear algebra class, and instead of belaboring an inductive proof of Cauchy-Schwarz, you can just show your students this and move on. That's a joke. So often these sum of squares proofs of little inequalities like this, the proofs themselves are not very insightful, and that's why I'm not going to do the algebraic manipulations. The proof itself here isn't very insightful, but what the key feature of it is that I had n variables, and the degree of the polynomials involved in the proof was a constant as n went to infinity, right? The degree of the polynomials involved here is 2. And what that means is that when I eventually go to use Cauchy-Schwarz to prove something much more sophisticated, when I use it inside here, it's not going to require me to use very high degree polynomials. That's good. I got to keep the degree down to stay in polynomial time. Okay. I think that is about all I want to say about robust mean estimation. So I will make sure that I think there should be a website with links, and we'll make sure that there's a link to notes that really give the proper sum of squares proof of this statement. But the high level picture is that because all the non-trivial inequalities we used have low degree sum of squares proofs, you can put those inequalities together to make a big but still low degree sum of squares proof of this claim. And you can plug this claim into the big SOS theorem to obtain a polynomial time algorithm for robust mean estimation. With that, I'm out of time, and I'm happy to take any more questions. Yeah. Yeah. Yeah, that just means that there should exist some x and z which simultaneously solve the system, which like make them all non-negative. It shouldn't be an empty. That is the original non-corrupted. Yeah, in our case, that'll be the non-corrupted samples and the non-corrupted mean. That's exactly right. And then also, I've got to set values for all the variables, right? So not just the non-corrupted samples and non-corrupted mean, but also the indicators for which samples were corrupted and the correct values for this slack matrix here. But yes, in the back, and then.
How long do these proofs actually take to generate computation?
How long do they take? Do you mean like if you're sitting at a whiteboard, or do you mean on a computer?
I mean on a computer, because the degrees of these polynomials are going to grow fast. I imagine if you just hand this to Mosek, it's going to freak out on you a little bit.
Yeah. Oh, okay. So I think that when the degree gets beyond about 4, we don't, and if the number of variables is growing, like in these high dimensional stats settings, we don't have solvers that are capable of handling these things. When the degree is 2, you're looking at basic semi-definite programming. Even semi-definite programming is relatively expensive, but you can probably handle systems with a few thousand variables. Notice that a lot of interesting inequalities are already available at degree 2, like Cauchy-Schwarz. So even if I restrict to the degree 2 sum of squares proof system, I can do a lot. In the case of robust mean estimation, it's actually possible to give a degree 2 proof, even though that requires a little bit cleverness, and it's the easier proof is at degree 4 or 6 or something. But let me point out two things that you can do on a computer that with current technology. One is that so in TCS and statistics, we're often interested in this regime that the number of variables is growing fast and the degree is pretty small. In applications like optimal control, they're interested often in the case that the number of variables is actually quite small, 10 or 20, because variables will correspond to like control points for a dynamical system. And if the number of variables is pretty small like that, you can actually afford reasonably high degree. And there's a package called SOS Tools that Pablo Perillo from here wrote and I think maintains that solves, that looks for sum of squares proofs of pretty high degree when the number of variables is reasonable. The second thing is that my view is that sum of squares as a tool for TCS algorithm design is a tool to understand the boundary between tractable and intractable problems. Like some problems in, say, high dimensional statistics or optimization just don't have polynomial time algorithms, we think. And this is a tool to explore which ones do and don't, and to discover, you know, the best polynomial time algorithms in terms of provable guarantees. Now, if you have some problem that you really want to solve on a computer that's not a problem you're studying for theoretical reasons, you would usually take some sum of squares based algorithm, and then you would open the box and you would start speeding things up in ways that don't work in general, but would work for the problem that you care about. So very often, you know, yes, the running time expressed by this generic theorem statement is very slow, but in many cases of interest, you can go under the hood and you can throw out lots of components of the generic algorithm that you don't need, and you can get things that run fast. So for robust mean estimation, we actually know algorithms that achieve this guarantee that run in nearly linear time. And you can derive those algorithms by doing just what I said. Open the box on this general theorem statement, use purpose-built solvers for the convex programs that are under the hood, and get fast running times. Yeah, one more, and then we got to move around.
The degree D in that theorem,
yeah,
degree, the highest degree that shows up in kind of
in the proof.
In the proofs, or is it the degree of the multipliers that you're expressing?
It's the degree of the whole expressions, any one of the terms that show up in the proof. So the multipliers, let's go back up here. Any one of these, the multipliers times the axioms. Yeah, and then I know you're next. Yes. Good. So this I had to leave fuzzy because I didn't want to do too much algebraic manipulation on the slide. So to build up a sum of squares proof, like eventually, I claimed, I did this little SOS less than thing, and then I said you can use that to build proofs like this, right? And what's going to ultimately happen is that as you chain together inequalities that are SOS inequalities, you're going to be accumulating all these squared terms that are your sort of leftovers from those inequalities. And all those squared terms eventually are going to wind up in this sum of squares polynomial. Yeah, so I'm going to, so I didn't show you how to use axioms. So I would do things like, I'm going to answer this a little bit briefly, and then we can do more detail offline because we need to let people go. If I have an axiom like P1 non-negative, and I want to derive some statement like A of x P1 of x less than B of x P1 of x. What I can do is I can derive a statement, and if I know that A is SOS less than B, I can get this statement as a sum of squares proof. Well, I need B of x minus A of x times P1 of x non-negative. This is the thing that I want to SOS prove this inequality. That means that I need to express the non-negative side as one of these products of axioms together with sum of squares polynomials. Well, I've got it right here. A being SOS less than B means this is an SOS polynomial. So this is some Q. And this is an axiom. So this is an SOS proof. is an SOS proof that P1 non-negative implies, A times P1 less than B times P1. Okay, so this is how I combine these SOS less than statements with axioms to derive further inequalities. And then you could use this statement, now I can just start using this as a black box, just like I used A less than B, and prove more stuff. Okay, there was a question here, and then we should go at noon, right, Piotr?
Actually, 10 minutes past noon.
10 minutes past? Okay. Yeah.
I guess my question was like, in the big theorem, do you have any intuition on like the proof itself explicitly, it's already having like 2D abstract,
Not if it's low degree. Not if it's, let's get the big theorem. Not if it's low degree, right? The proof itself has like n to the d terms. Good, great question, yes. Yeah.
And then if you didn't move, can the algorithm begin faster?
Good question. So on some level, in these in these robust stats problems, in these stats problems in general, like where I'm looking for some unknown thing, it doesn't make so much sense to talk about, like if I knew the proof already, the proof somehow has baked into it the guy that I want to find, right? The unknown thing I want to find. So for this application, if I knew the proof already, it's not so interesting to run this algorithm. But that being said, it's still a very good question about, does the algorithm find the proof? The answer is not really. So what's going on here? If I have a statement, a polynomial inequality, and if I would like to know if there is a sum of squares proof of that inequality, there's an algorithm to do that. It runs an n to the d time. So n is the number of variables, d is the degree. So if I tell you some polynomials, I ask you, is there a sum of squares proof that this one is less than this one, when all these other guys are non-negative? You can run a big semi-definite program, and it'll say, yes, there is a proof of degree at most d, or no, there's not a proof of degree at most d. That's often a useful primitive. It's just not the primitive that we're using here. Because here, I don't know the polynomial inequality that I would like an SOS proof of, right? That polynomial inequality involves, on one of its sides, where'd it go? That inequality involves the thing I don't know. So what role, then you might ask, what role does the existence of the SOS proof play in the algorithm if under the hood the algorithm's not finding the proof? The existence of this, so what will happen under the hood is that the algorithm solves a convex program. So it will solve some convex optimization problem. And when you solve convex programs, so the algorithm's going to search over some convex set. It's going to find a point in that convex set. I didn't describe what that convex set is to you. Maybe you've heard this funny word called pseudo distribution. If you've ever heard about SOS before, and the convex set is the set of pseudo distributions, but don't worry about it. It'll solve for a point in a convex set. And what you want is that any point in that convex set is good for you, right? You want that convex set contains only points that you like, that are close, in this case, maybe close to this thing you want to output. How do I know something about points in a convex set? Well, to know things about points in convex sets, I trace out the convex set with hyperplanes, right? I look at the dual of the convex set. And what's happening under the hood is that these sum of squares proofs can be translated into duals to the convex set that the algorithm is going to do its search in. So these proofs are witnesses that any point in that convex set is good for you. Yeah. It's exactly that. Bingo.
But then, if the set was empty, which is what would happen if there is no solution, there's that mean that the algorithm is never going to work if there is no solution? Would that
Let's be slightly careful. If there's no solution, so let me draw this picture. So now we're sort of going under the hood of this theorem statement that that I black boxed, which is fine. It's an interesting statement. So what is this? Remember way back at the beginning, I said that SOS was a hierarchy of convex relaxations. So what is this convex set? Well, we have our semi-algebraic set. It's carved out by the polynomials. The convex set that we're talking about is like one of these relaxations. Maybe it's the degree, degree equals 10. I don't know, relaxation of that set. The proofs are the hyperplanes that bound this set. So these guys are SOS proofs. And I wanna pick on you and correct one thing you said, because it's an important distinction. If this blue set is empty, it does not necessarily mean the red set is empty, right? Because it's a relaxation. Okay, and that's exactly for the same that statement. So one of the cool things about this area is statements about convex sets get translated back and forth into statements about polynomials, and you get to use whatever language is most powerful for the application at hand. That statement is the same as saying that not all degree D polynomial inequalities have degree D sum of squares proofs. That's the dual version of that statement. So one thing that you get to do in this area is get very facile with this translation between convexity and polynomials. Anyway, your question was, is it useful to know that the set is empty? Is that right? Yeah, so that can be very useful. So one thing you might want to do is use sum of squares to solve some combinatorial optimization problem. Maybe I want to use sum of squares. So this is not in really the stats domain, but maybe I want to use it to find a cut in a graph that cuts a certain number of edges, right? That cuts a large number of edges. I want to solve max cut, let's say. Well, I could do this thing I did before. I would set up a polynomial system that says, please find me a partition of the nodes of this graph into two pieces so that the number of edges crossing is at least 99% of the edges of the graph. And if sum of squares can tell me if the non-convex set that polynomial system describes is empty, that means that there's no big cut in the graph. If the convex relaxation is empty, that's something I can actually detect in polynomial time. If the convex relaxation is empty, that gives me a way to tell whether that there's not a cut that cuts 99% of the edges. Actually a crucial problem in combinatorial optimization, this max cut problem, the complexity of the max cut problem, is intimately related to this question of whether there exists sum of squares proofs about whether or not there exist cuts that cut large number of edges in graphs. So that's how you would use sum of squares to do something like solve a combinatorial optimization problem. It's a little bit twisted. I apologize. I'm happy to clarify that afterwards. A little extemporaneous. Okay, thank you all for your attention. I really appreciate it. Have fun with the guy in the afternoon. Have a nice lunch.